Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 3 for this week, and it's part 2 of a two-part series on how weather data is coded and then sent to meteorologists all over the world. On Wednesday, we talked about surface data. Today, we're going to talk about upper air data, what the weather balloons collect as they go up through the atmosphere and collect data as they go. So let me go on ahead and put myself down here in the corner and let's get started. This is a sample report from, it's an actual report, but I'm using it as a sample, from Greensboro yesterday morning, okay? And so all of those numbers represent different types of data about what the weather balloon is finding as it goes up. And so let's take a look at some of them. I'm not going to go through every single block of numbers, but the more significant ones. So the 72317 is basically the station identifier for Greensboro. The 72 indicates a certain block of stations. There are these blocks of stations all over the world, and Greensboro is in the 72 block. And then the 317 is the actual identifier for the Greensboro station, okay? Now, just real quickly, the numbers or the set of numbers before that, and again, don't ask me who came up with this system. The 74, you subtract 50 from that to get the date, which is the 24th, or was the 24th. And then the 12Z is the time, that's 12Z Greenwich time. And then the 1 indicates mandatory levels all the way up to 100 millibars. All right. The 99 indicates surface data, okay? And then the 992 is the station pressure in millibars, okay? It is not reduced to sea level. And so if you were out of Denver, that number might be in the 800s somewhere because they're a mile above sea level. So this is the actual pressure not reduced to sea level. And by the way, just to refresh all of our memories, is that the reason that we reduce the pressure to sea level is that if we didn't, then all the lows would be over the mountains and all the highs would be over the ocean. And we want to know where the weather systems are, so we have to establish a standard by which all of these observations, no matter what elevation they have, are going to meet, okay? And that tells us where the actual highs and lows are. Okay. The 172 is the temperature in tenths of a degree Celsius. So the temperature is 17.2 degrees Celsius, which is about 63. Now, if the number after the decimal point, which would be the 2, if that number is even, then the temperature is above 0. If it's odd, then the temperature is below 0. So if that was 171, that would be minus 17.1. So with this kind of a system or coding, it's never going to be more than a tenth of a degree off from what it actually is. And the 11, I'm sorry, I'm getting ahead of myself. The 11 is the dew point depression in tenths of a degree Celsius. So the dew point depression is 1.1 degrees C. What is the dew point depression? Is it a dew point that's having a bad day? No. You then subtract 1.1 degrees C from 17.2 to get the actual dew point, which would be 16.1, okay? So you have a dew point, you have a dew point depression, you do the math, and then that gives you the, you have the temperature and the dew point depression, you do the math, and then you get the actual dew point. Okay, the 14005 gives you the wind direction and the wind speed. The wind direction is 140 degrees or southeast, and then the 5 is the wind speed at 5 knots. Now we go to the 00203 group here. The 00 indicates the data is from 1,000 millibars, a constant pressure surface, and that's the way we look at maps. There's 850 millibars, 700 millibars, 500 millibars, and so forth. So the 00 means it's from 1,000, and the 203 indicates the height above sea level in meters of the 1,000 millibar surface. So it's 203 meters above sea level. Okay, now, if everything after that is a series of slashes, then the 1,000 millibar surface is underground, and an estimate of the height above sea level is made. Now, you might think this is absolutely crazy, but If you're looking at, say, the 1,000 to 500 millibar thickness, which gives you the average temperature of the air between 1,000 millibars and 500 millibars, then you have to have this number, even if it's underground, for you to be able to accurately assess what that average temperature of the layer is, okay? So there's a formula that is used to come up with that number, but again, 203 meters above sea level, but the surface itself is actually underground. Okay, now all of the levels above 1,000 millibars follow the same format, so I'm just going to take a look at a couple of them. I'm not going to go through every level. So this group here is the 925 millibar group, okay? And again, it shows the height above sea level of 866 meters, okay? The temperature is plus 13.8 because the 8 in the middle is even. If it was 7, then it would be minus 13.7. And then the dew point depression is 1.1. So you do the math, 13.8 minus 1.1, and you get a dew point of 12.7 degrees C. And then the wind direction is 115 degrees, and the wind speed is 10 knots, okay? Now, let's jump to the 200 millibar surface, which is way, way up there, okay? So the height above sea level, and when you get into these higher levels, you have to add digits on the front side and the back side, and it's different for every level. But just take my word for it. In this, it is 12,080 meters, okay? So you put a 1 in front of the 208 and a 0 after the 208 to get that height. The temperature is minus 64.1 degrees C, okay? That's what happens when you're up at about 35,000 feet. And then the dew point is minus 68.8, which again is minus 64.1 minus the dew point depression of 4.7. The wind direction is 270 degrees due west at 44 knots. And, you know, in the wintertime, sometimes at this level, you can have wind speeds well over 100 knots, okay? So you get some pretty spicy winds up at those heights. Okay, the 8.8 in this group represents the data from the tropopause. What is the tropopause? It is the top of the troposphere, the boundary between the troposphere and the stratosphere, which is the next level above it. The tropopause is defined as the level at which the lapse rate of temperature, in other words, how the temperature is changing with height, is 2 degrees C per kilometer or less. So normally the temperature decreases with height as you go up, but usually at a faster rate than this. As soon as it gets to 2 degrees C per kilometer or less, then that is defined as the tropopause. And in this case, it is 175 millibars. The 77 represents the maximum wind data. Unfortunately, in this case, it is missing. That's what the 999 means. So we don't have any maximum wind data for some reason, not sure why. Here, in the 45408 group, the first 2 digits after the 4 are supposed to show the absolute value of the vector difference between the maximum wind level and 1 kilometer below that level, okay? But since the data is missing, it's really sort of a useless set of numbers in this particular case. And then the next 2 digits after the 4 are supposed to show the absolute value of the vector difference between the max wind level and 1 kilometer above that surface. And then the 51515 indicates that there is supplemental data about to come your way. The 10164 indicates the next set of numbers are a measure of the lifted index. Now, if you remember, you have the sounding, the actual values of the environment. And then if you take a parcel, an air parcel of the ground, and it becomes buoyant, then it starts to rise, and when it becomes saturated, then it doesn't cool at as quick a rate because the saturation process is reducing heat, okay? So that air parcel gets up to 500 millibars, and we're taking a look at the difference in temperature between that air parcel and the actual environment. And if that number is negative, that means that the air parcel is warmer than the environment, and it's buoyant, and it's going to keep accelerating upward, okay? So, in this particular case, the lifted index, again, is the difference between the environment and a parcel lifted to 500 millibars. And here you see 0.00003. This represents the lifted index in tenths of a degree Celsius. And since the number is odd, the lifted index is minus 0.3. If it was 0.0002, then it would be plus 0.2 degrees Celsius. So in this case, if you lift a parcel to 500 millibars, then it is going to be buoyant and will continue to accelerate upward. 10194 indicates data from looks at the mean wind from the surface to 5,000 feet and from 5,000 feet to 10,000 feet. So in this case, the mean wind, the average wind in the lowest 5,000 feet is 105 degrees or just south of due east at 7 knots. And then the mean wind from 5 to 10,000 feet is 250 degrees or west to west-southwest at 6 knots. Oh, and that is it. That's probably more than enough. But that's how the data gets to us. And again, when I was in school, we had these skew T-charts that I've showed on here before, and we would actually look at that data, decode it in our mind, and plot it. And of course, now you have computers that will do all of that for you, but I would still argue when you do it by hand, you know that data better than you're ever going to know it. So, all right, folks, I'm sorry if that was torturous. That is bonus weather video number 3 for this week. I hope you have a wonderful weekend. Of course, the next daily update will be coming up later this afternoon. I'll be doing it from the road. And that's really about it. So have a wonderful Friday, an even better weekend, and we'll talk to you later today. See you later, everybody. Bye-bye.